Welcome back to Lesson 4 quiz, and we're going to start on number 9. If the calculated deflection of a steel beam is excessive, it is necessary to select a different beam section having a greater moment of inertia. I know this one right off the top of my head, but let's go over all of them. Area. Could that necessarily be true? Yes, because the greater area would give you a greater moment of inertia if you have more area away from it, but that's strictly moment of inertia. Greater section modulus, yes, that would help you, because typically something has a greater moment of inertia will have a greater section modulus. So it's always a little bit confusing. And then if a calculated deflection of, actually D would work too. So you could justify all these in your head. Obviously A is the furthest off. B you could justify. D you could justify. The best is going to be C though, because you want to have the greater moment of inertia. Will give you less deflection. Because let's look at the different deflection. Actually, let's go do this real quick. Go to your beam diagrams and formulas, and let's just look at some of the deflection equations. And we remember that, or if you don't remember, go to page 2-296 in your steel manual. You will see that for a uniform distributed load, which is case number 1, you have max deflection equals 5 WL to the fourth over 384 EI. And this is why I didn't like that question, and I don't like typical, because if you selected something with a higher what I meant to say E, modulus of elasticity, it would actually decrease your deflection. So that's a correct answer. I wouldn't, if you said, oh, I'm just going to increase the modulus of elasticity, I'd be like, well, theoretically, that's correct. That is a correct answer. So, but realistically, you have steel. If you can go ahead and tell me, it says deflection of a steel beam. What else are you going to use? I mean, typically, the modulus of elasticity of steel is going to be 29,000 KSI, and concrete's around, let's say, 3,700 KSI, so 29,000 or 3,700. So you're using steel already, and it's pretty much got the highest E. So that's why I is the better answer. And let's look at simple beam case 2. You can see that this is the load increasing uniform to one end, and it's delta max equals W, it's actually 0.01304 WL cubed, I think, over EI. And once again, you have EI on the bottom, so either of those would be, or I, it's always going to have EI on the bottom. And that's just what your deflection equations look like, and meaning you want to get a greater moment of inertia. So C is your answer for number 9. And moving on to number 10, it says select the incorrect statement about the composite design. Remember, composite design is when you're typically, you'll have, and this is typically, once again, this is not the only composite. Composite just means two things combined. But you'll have your top flange embedded in concrete, or sometimes they have these. They actually have excuse me. They'll have T's, and this will be embedded in concrete. They have these now, and sometimes you'll, looking at a more elevation instead of a cross-section view, here's your bottom flange. And sometimes they'll make it like this. So, or some sort of pattern to where it connects to that concrete a little bit better. All right, I don't remember what I was talking about. A little bit of a tangent there. So that's composite. I was explaining what composite was. That's what you're probably going to get most of all, is a concrete and steel put together. A composite beam All right, let's go over to A. A composite beam consists of a steel beam and a concrete slab that act together to resist bending stress. I would say that that is correct. Typically, you're going to have that concrete's going to be compression. Remember, you're going to have positive moment. Positive moment means your bottom's going to be in tension. So steel's good in tension, concrete's good in compression. I would say that is correct, but we're looking for an incorrect. So A is correct. So like, mark that off. That's wrong. That makes any sense. A little confusing. Let's go to B. Because of the stiffness of a composite beam, it is unnecessary to calculate deflection. And I would say that is incorrect because, and they've said actually in the study guide, but you want to, usually these will be stiffer. I agree. The composite beam will be more stiff, but since it's going to be more stiff, you can actually make it, you can push it a little bit more. But that is incorrect. So B is definitely incorrect. I'm going to circle that. I'm going to go on to the other ones, just make sure that these are correct. Shear stress between the steel beam and the concrete slab is usually resisted by welded studs. Sure, yes, you could say that's correct. So I would mark that off. In composite design, the concrete slab effectively becomes part of the beam's top flange, and that would be correct as well. So it is B. The B is incorrect, which means it's the right answer. I hope that's not confusing. This will usually be your compression flange. This will be your tension flange. And together they kind of form a moment couple, a force couple. I guess you call it a force couple. And I kind of explained that once in the structural analysis of a simple truss. Excuse me again. And hopefully that makes sense. Everything in bending will form a force couple, but it's actually more of a stress distribution or something. It's going to be like this. Because your top flange is so wide, usually it'll push. You'll use more of this steel, and if that makes any sense, it'll kind of look like your stress distribution will look like this, and it'll be bigger at the bottom because you have a greater width. This is PS over PSI or KSI. It'll make this be smaller, and it will force your neutral axis up further. So your neutral axis was probably going to be right here. And typically in this type of design, you'll probably want to keep, well, I'll just stop right there. Your neutral axis will be right there, or it may even be so far as up here, because you may want all of your compression flange. You want your neutral axis to be in your compression flange. And that's kind of depending on the design you want to do, and that'll be in your code book. All right, and that is the end of the quiz for lesson 4. And once again, the answer to number 10 is B. All right, I hope this was helpful, and I will see you for lessons 5.